Oh, there's a chat that says great title slide.
Yes, I saw that pop up. Thanks.
So we'll give 2 more minutes and then start. But assuming that timing is not overly tight. Yeah, 2 more minutes.
I think it should be okay, yeah.
Okay, so good morning, everyone. I'm excited to have Jack Hessel to give a talk today. Jack is a PhD candidate at Cornell University, working with Lillian Lee, but often collaborating also with David Mimno. And his primary research field seems to be in NLP, but what's interesting about Jack's research is that it's very diverse in the way that he puts together techniques from different fields, including not just NLP, but also computer vision, and then addressing questions that are related to human communication and social interactions. So today, the talk is going to be about the promise and the perils of learning grounding from visual-textual web data. And about the questions, we are going to take that toward the end of the talk. So please hold that during the talk.
Awesome, great. Thank you so much, Yejin. I'm super happy to be at least physically here in spirit, but certainly virtually here, to talk about the promise and perils of learning grounding from visual textual web data. I do want to say, just as a technical note, if anything is going awry, do feel free to interrupt me. I would very much appreciate it. Great, so yeah, let's get started. Yeah, so I'd like to start out by motivating this field sort of more broadly. So yeah, what is visual textual grounding? There are lots of possible definitions, but one sort of machine learning centric one that I'm fond of is that visual textual grounding is a collection of tasks that require connecting visual and textual content. To give a few compelling examples of tasks of this flavor, I'll show you them now. One is alt text generation. So this is the caption generation task with, it's sort of a popular image text task. The idea here is that we would like to build machine learning models that process the visual content of an image, maybe the literal objects and actions, and generate a caption based on those detections. This is useful for blind and low vision users who use screen readers to browse the web. Similarly, as robots become increasingly present in our day-to-day lives, there are awesome opportunities in human-robot interaction for visual textual grounding. In particular, we'd like to be able to interact with robots using natural language instructions, such as here are the yellow ones. And we'd like that robot to be able to take that natural language, parse it, and then map it onto the physical world. Usually, robots interpret the physical world through cameras, so a visual textual grounding task. And finally, there are some really compelling use cases within web video parsing. I don't have time to get into the details of Kim et al.'s work, but essentially what they showed is that if a user is watching an instructional video, if a sort of annotated timeline of that instructional video is presented alongside it, user experiences are greatly improved. And to deploy a tool like this at scale, we need automated tools that can process visual content within these videos. So why are visual textual grounding problems interesting AI problems? I'd like to present this example from Zhu et al., not only because it's quite funny, but I think it's also a sort of compelling example. Once I displayed this image on this slide and you processed it, you probably started making certain inferences about the scene. So perhaps the physicality of the scene, indeed, it's a dog riding a surfboard. There's a wave in the background. And almost automatically, subconsciously, without even thinking, you've learned a lot about this image. And indeed, we can test computers' capacity in this regard by asking questions about this image. So we might ask simple questions about the objects within it. So like, what is the dog doing? The dog is surfing. This is a very easy question for us. And indeed, all of these questions are probably really easy for us as humans to answer. I think for this particular task and data set, human accuracy in this question answering setting is around 96%. But if you break down the sorts of reasoning that are involved here, it's actually quite complicated, right? So for each of these questions, we have to parse the natural language. For the image, we have to construct some representation of the visual content. We have to find a mapping between these two processed forms. So we have to map perhaps objects onto the scene. Sometimes we don't map objects onto the scene though. So take, for example, the question, where does the scene take place? There's no like direct mapping between, like nouns in this sentence and objects in this image, and yet we're still able to make a connection between these two very easily. And then on top of all of this representation learning, we then have to use our common sense to know that, this is probably happening at a beach because that's where surfing happens, and that waves are the reason that foam might exist, and so on. And so I chose this example not because I think this is the most sophisticated, cutting-edge question answering task, but because it's an example of a slightly older task that still has a huge gap between human performance and computer performance. So again, humans get around 96% or so, whereas computers get around 72%. So I think there's a lot of really interesting AI problems in this domain. Indeed, though, I think visual textual grounding is important beyond AI. In particular, cognitive psychologists have been studying this sort of thing since at least the 1970s. And indeed, cognitive scientists have been studying the symbol grounding problem for quite some time as well. But this talk isn't solely focused on visual textual grounding. It's in particular focused on learning visual textual grounding from web data. So I'm going to motivate the consideration of web data for these sorts of tasks. In particular, I think one reason why web data is particularly compelling is because it's like unreasonably effective at producing state-of-the-art performance on different benchmarks. So indeed, Halevi, Norvig, and Piera in 2009 called web data the best ally we have for a lot of very difficult AI problems. Does this observation from 2009 hold true today? Yes, mostly. So if you look at a very broad range of tasks I put up on this slide here, I've put multimodal tasks dealing with image and text understanding, different video and text tasks, and even unimodal tasks. Despite the great diversity of different reasoning that's required for these things, a similar pattern emerges. If you want to get state-of-the-art results on these things, you pre-train representations on usually a very large unlabeled web corpus, and then transfer those representations that you learned onto these downstream tasks. And this recipe has, in recent years, proven quite effective for pretty much every benchmark task there is out there. And so because web data is usually the source of unsupervised pre-training, you might be interested in it from the perspective of getting good performance on tasks. But I think even if you're not necessarily the most interested in getting state-of-the-art performance numbers on different tasks, I think studying multimodal web data is quite important given the changing nature of today's web. In particular, here is a plot we made that plots the proportion of different types of submissions that were made to reddit.com dating from 2005 to 2013. And the particular line of interest for today's talk is this blue line. which represents the proportion of posts that are media-related posts. So these are images and videos and so on. And you can see from 2005 to 2013, there's sort of this meteoric rise in the frequency of these sorts of media posts. So indeed, the web is becoming increasingly multimodal. This pattern isn't limited to just Reddit. This is true on Facebook. This is true on Twitter. This is true even in these sort of new platforms that are solely focused on multimodal content, like Instagram and Snapchat. And I think I'm too old to know about this, but I've heard of this thing called TikTok, where people are posting videos as well. And so indeed, the web is becoming an increasingly multimodal place to communicate. A pessimist might look at a graph like this and think that perhaps this is indicating something quite bad about society. So like, is this the end of the world? Are we just looking at more cat pictures and watching more YouTube videos and not discussing, serious, important news topics? I'd like to paint a slightly more optimistic view of what's going on here. And in particular, I'd like to invoke the field of semiotics, which is this field that's related to linguistics. And semioticians are quite interested in the multimodal nature of communication. So a semiotician might point out that there's a reason we're doing, for example, this talk on a video call versus me just writing up a transcript and emailing it to all of you. I'm using my hands to communicate. I'm using my prosody to communicate. And indeed, yes, semioticians argue that communication is inherently multimodal. And for most of human history, like we haven't been sending emails to each other. We've been talking face to face, and there's a lot of multimodality in that context. Good. So I hope I've motivated not only the area of visual textual grounding as a set of really interesting problems, but also the consideration of multimodal web data. And I'd like to concisely sort of state my research goals at this point. I have two main research goals. My first research goal is a machine learning research goal, and that is to build better grounding algorithms. I want to build algorithms that can reason cross-modally, that are useful for compelling downstream applications. And my second goal, which is kind of more of a computational social science goal, is that I really want to understand web communication. And these two goals might seem disjoint at first, but I find them to be linked in a very compelling way. In particular, to understand web communication as a computational social scientist, I would definitely need better grounding algorithms than we have today. So more and more of our communication is multimodal, and thus we need algorithms that are capable of cross-modal reasoning, incorporating real-world knowledge, including common sense knowledge and background knowledge, to process the social context of these different sorts of communication. So we're not quite there yet on the algorithmic side. Conversely, I think that because web data seems to be quite effective at achieving state-of-the-art numbers and different performance benchmarks, in order to build these algorithms that we're going to need to honestly reckon with the fact that web communication is its own sort of beast. And so to design more unsupervised training objectives for this sort of data, we're going to have to, I think, look to different theories of communication if we are to leverage this data to learn good representations. These dual research goals that I have led me to contribute a variety of works in this, I would argue, like increasingly large intersection between natural language processing, computer vision, and computational social science. Good. And so with all of that, I would like to sort of dive in a bit more to a few projects that I have time to talk about today. And in particular, the rest of this talk is organized into two parts, the promising part and the perilous part. If you get nothing else from this talk, I think this is the thing that I would like you to get. In particular, the promise of multimodal web data is that we can do a lot of really cool things with it. We can set state-of-the-art benchmarks with things. We can build all sorts of very practical tools with it. But the perilous part of this promise is that web texts are not literal image descriptions. When someone pairs an image with a piece of text, it's a very conscious choice. And despite the fact that most of our algorithms treat web text as literal image description, or they sort of don't really reckon with the communicative goals of that image text pairing, I think to move forward in this field, we're going to have to address this in a more head-on way. Good. And so with that, I'll jump into some of the particular projects that I have time to discuss today. I'm going to first discuss a project that was published at EMNLP this past year about learning from multi-sentence, multi-image web documents. To give a little bit more background about this particular setting, folks who are familiar with image text grounding work are probably familiar with the image captioning case. There's a number of really awesome data sets of this form that are out there. In particular, they consist of images paired with literal textual descriptions of those images. So for example, this image of an airplane might be paired with the caption, "There is an airplane on a tarmac," for example. And a lot of the algorithms in this area are based on data sets like these. And we've had a ton of success in learning different correspondences between natural language and images in this setting. Unfortunately, the web doesn't really look like the single image, single caption case, right? So if we're going to leverage web data to learn good representations for downstream tasks, we're going to have to rely on weaker forms of supervision compared to this annotated case. And in particular, the setting that we're proposing is to look at documents that contain multiple images and multiple sentences with no explicit links between single images and single sentences. And our goal is going to be to learn the same sorts of grounded information that we might be able to learn in the captioning case from these noisier web documents. If it helps to have a running example of multi-image, multi-sentence documents for this part of the talk, I like to think about Wikipedia articles and the images and sentences that they contain. Good, so what are we going to be doing with these documents? Well, we want to learn some interesting representation at training time. So we assume that we're just given a bunch of multi-image, multi-sentence documents at training time. But at test time, we're going to evaluate the learned representations on a link prediction task that asks our algorithms to find single image, single sentence links within the same document. So for a given document at test time, we're going to be predicting links between single images and single sentences. This is a pretty difficult task because we have no explicit labels at training time of the form that we're predicting at test time. So this is hard because there's no annotation. Similarly, when we start looking at web documents of this sort, we start running into some of the problems that I alluded to before. In particular, we may run into like a sparsity concern where there are sentences in these documents that do not refer to any image. So if you're looking at Wikipedia, it's obviously not the case that every sentence is like literally describing a particular image. So there's this sort of sparsity problem. And similarly, there's interesting plurality problems as well. So sentences may refer to multiple images, possibly in indirect ways. And so this is very much a not one-to-one task. But nonetheless, despite this difficulty, we think this is a very promising pre-training framework. If you could learn strong representations in this setting, you could do all sorts of cool things. For one, this setting scales very easily. You can sort of arbitrarily download as many documents of this flavor as you would like. And in particular, this appeal to scale also holds for resource-restricted domains. One domain that I looked at over the course of my PhD for computer vision and natural language processing work that I think is very cool is historical books. So we were looking at this corpus of like books from the 1800s and before, and we have OCR that can recognize the characters, and we have images within those books that can be segmented, but the mapping between them is not possible these days because we don't have great computer vision models for representing historical images. But we do have a lot of documents of this sort, and if we could learn nice representations, this would enable computer vision in all sorts of new domains. I'd also like to motivate this sort of test time task. So recall that we're evaluating our algorithm's representational capacity by performing a link prediction task at test time. And in general, I think this retrieval task, this same document retrieval task, is it's pretty compelling for alt text generation in practice. Take this image, for example. This is an image of a painting, a famous American painting of Washington crossing the Delaware. Now, if you were to hand this image to a state-of-the-art image caption generation model trained with a generation objective, it might output something like this. I think it's a group of people riding on the back of a boat. I'm not trying to downplay how very cool it is that CaptionBot was able to, recognize that there's a boat and some people and they're riding on it. But like, I feel like this image is much more than just a group of people riding on the back of a boat, right? Like, this is not just people on a boat. This is Washington crossing the Delaware. And generative objectives, while I think in the long term for AI, they're sort of like the right thing to shoot for, if we wanted to generate an alt text for this image today for, say, low vision and blind users, a retrieval objective is quite compelling. If you go to the Wikipedia article for this particular painting, you'll find this sentence: General Washington is emphasized by an unnaturally bright sky, etc. And I'm not saying that this particular caption is better in all contexts, but what I am saying is that in some contexts, this perhaps more context-specific description is potentially more compelling. And indeed, we didn't have to generate the sentence. We just had to retrieve it from the nearby article. So again, I think generation is very cool, and I think a very good AI problem in the way we should be going. But I think in practice, if you were to deploy a system, you might consider a retrieval system. Good. So a little bit of information about the data sets that we looked at for this particular paper. I don't have time to talk about all of the data sets here. I'm going to mostly be focusing on the Wikipedia case. And in particular, the Wikipedia corpus we looked at has 14,000, or I guess 16,000 documents total. Each document contains roughly 86 sentences per document and roughly 5 images per document. So how are we actually going to do this unsupervised learning task? It's 2020, so we will be using neural networks for this. I'll walk you through the forward pass here in 1 second, but I want to say that this training process is modulated by this function that computes a similarity score that represents how similar the model believes a set of images is to a set of sentences. So given a set of sentences and a set of images, this part of the model outputs a similarity score saying like how similar the model believes these two things to be. So what are we going to do here? Well, we are going to pass all of our sentences through a recurrent neural network to extract feature vectors, and similarly pass all of our images through a convolutional neural network to extract feature vectors. Between these feature vectors, we're going to take the pairwise cosine similarity between all of them to form this M hat I matrix. Each entry of this M hat I matrix corresponds to the model's belief of and strength of an association at this particular point in training. So if an entry is high, the model believes that a particular sentence is associated with a particular image. We're then going to treat this M hat I matrix as weights in a bipartite graph between images and sentences. And indeed, it's this M hat I matrix that we're going to be evaluating at test time. But at training time, we need to get a training signal to train the parameters of our recurrent neural networks. So what we're going to be doing, at least in our best performing model variant, is doing a little bit of structured prediction. In particular, in the forward pass of our neural networks, we're going to solve a bipartite assignment problem between sentences and images. And if you think back to, perhaps if you haven't seen bipartite assignments in a while, if you think back to your intro graph theory class, a bipartite assignment is a discrete optimization process by which you select entries of this matrix to maximize a similarity score, subject to the constraint that a single image can only be assigned to at most one sentence and vice versa. Good. So in the forward pass, we actually do literally compute as a layer in the neural network a bipartite assignment. We get a similarity score. And then in the backward pass of these neural networks, we backpropagate through the score of that assignment. I'm happy to chat more about this after. This training process has a close connection to the structured perceptron, if you're into that sort of thing. But I don't have time to go into too much more detail here. But I will talk about the meta training process. So we have this similarity score assigning neural network. What are we going to do with it? Well, we're going to be training with max margin loss coupled with negative sampling. So the training process goes as follows. We're going to gather sentences and images that truly co-occurred within the same document. And we're going to try to maximize the similarity between truly co-occurring pairs, while simultaneously minimizing the similarity between negatively sampled image sets and sentence sets. So for this particular set of sentences, for example, we will negatively sample images from different documents, image sets from different documents, and minimize those similarities. And so this is just a high-level sketch of how the training process goes. And we're going to maximize this training objective with respect to the parameters of our neural networks. We do have some quantitative results here. So I haven't talked about these two data sets or these evaluation metrics. These are sort of standard link prediction metrics of AUC and precision. our algorithm outperforms some, we think, reasonable baselines, such as random guessing, which, okay, it's a good sign we're outperforming random guessing, but also an object detection baseline and a version of our algorithm that does not use structured prediction. But what I think is more instructive than looking at numbers and tables is actually examining model outputs. So here's an example of our model's prediction on a 100-sentence article about Mauritius, which is a country probably best known, at least in the West, for being the former home to the now extinct dodo bird, which is this flightless bird pictured right in the middle. And you can see what our model is predicting here. So in parentheticals, we have the cosine similarity multiplied by 100. So this is sort of a measure of confidence. And we're doing pretty well, right? So like we get an image of an island and we get archipelago, we get a beach and we get natural beauty. And indeed, we do match up the dodo with a sentence about the dodo, despite the fact that only 2 sentences in this article mention the dodo. So for high confidence predictions, we're often doing quite well. In contrast, if we go down the list of confidences in terms of predictions, you can see that we're starting to get some weird stuff, right? So here we have this image of a building with a field of grass in front of it, and our algorithm has selected the sentence that mentions field, but it's field in a different sense of the word. So perhaps there's some word sense disambiguation that's not happening properly here. And indeed, by the time we get to like this least confident prediction, we're forcing the algorithm to align this sort of segmented map of Mauritius with a sentence in the Wikipedia article. And it's not clear like if this task is even possible, first of all, or like what the appropriate matching would even be. And I think this is pointing towards the second half of the talk, wherein I'll discuss why web text should not be viewed as literal image description. Good. So some promising preliminary results. In the future, I'm looking forward to scaling up this learning setting to see if indeed our representations get much better with scale. I'd like to shift gears a little bit, at least in terms of the modalities that we're considering. In particular, I want to briefly highlight some previous and ongoing work I have with some collaborators at Google about learning from web videos. The main rationale for talking about this work very briefly is to show that I'm not just interested in static images and static sentences, but also interested in web videos. Indeed, the task that we looked at in this video case was a captioning task. Again, I don't have time to get too much into the details, but the idea is that you want to generate a natural language imperative description for particular temporal segments of different instructional videos. So from 21 seconds to 51 seconds, the goal is to generate the caption, grill the tomatoes in a pan and then put them on the plate. When we had done this work, it was from the computer vision community, and prior models had just examined the visual content of web videos to do this task. But we thought, and a lot of prior work suggested, that if you not only look at the visual content, but also the automatic speech recognition tokens, you might do a lot better at this generation task. So when people are cooking, they're talking about what they're doing, and YouTube picks up on this and generates these sort of noisy ASR captions. And we thought, why not throw these into a sequence-to-sequence model and see how it does. Here are the high-level results. Again, higher numbers here are better. These are automatic machine translation metrics. The previous state-of-the-art at the time we wrote this, which was a video-only model, gets the first row of numbers. And in contrast, if you ignore the video content and just look at the ASR, you do much, much better. So indeed, this suspicion that we had proved to be correct. And also excitingly, if you combine the visual content with the speech tokens, you do even better. So yeah, that was kind of a very fast whirlwind tour of some work I'm quite excited about with my collaborators at Google. We're looking at tasks beyond just caption generation as well, but I can't quite talk about them yet. Cool, great. So I guess that kind of concludes the first part of the talk. Indeed, the uniting factor between both the multi-image, multi-sentence document work and the web video work is that they're quite promising, I think. We can learn cool representations from weak supervision settings, and also like we can do cool caption generation with noisy web data. So these are both very promising. But yes, to shift gears to the more perilous part of this talk, I'd like to highlight what I see as the biggest impediment to learning from large-scale web data in this setting. And in particular, I think Microsoft Cocoa, despite the fact that I love it as a data set and I work with it a lot, it kind of embodies this literal description problem. In particular, Microsoft Cocoa and a lot of similar data sets were gathered using explicit guidelines of explicit, like literal object action annotation. So crowd workers were told to write captions about images that were very literal. So much so that Microsoft Cocoa, the Microsoft Cocoa folks literally described this annotation guideline to folks. They said, do not describe what a person might say. So if you've been wondering why Microsoft Cocoa captions are oftentimes a little bit inhuman, it's because they're purposefully designed this way. And a lot of the algorithms that work very well in MS Cocoa, if you apply them to noisy web data, they don't work quite as well. And so I think we're going to need to slightly rethink these sorts of algorithms that we apply to the sort of more in vivo web settings that I think we're going to have to consider going forward. So I'm not the first person to point this sort of observation out, that web text is not literal description. Marsh and Domus White in 2003 asked, how does an illustration relate to the text with which it is associated, or what are the functions of illustration? So there's this notion that web communication is quite deliberate. There's a reason why people select particular sentences and captions, and there's a reason why people select particular images. Their answer to this question was essentially that there are lots of different ways that images and text can relate on the web. So they developed this taxonomy where they argue that text can decorate images, text can organize images, and so on. And so lots of different relationship types. And while I don't advocate for this particular taxonomy, or really any particular taxonomy, because I think it's a little bit inflexible for different context-specific communicative strategies, I do think the idea of an underlying typology to these types of communications is quite compelling. And indeed, these two projects I'm going to touch on today are all about examining image and text communication on the web beyond just literal description. The first of these projects aims to put a number to this intuition that we have that images and text may literally overlap to different extents in different contexts. Here's a motivating quote from Helen Kohornen. This is a quote from 2014, and a lot of work has gone on since then, obviously. And while I think this isn't as true today as it was then, I think there is still something quite compelling about it. In particular, Helen Kohornen in 2014 argued that performance advantages of multimodal models over language-only ones have only been clearly established when models are required to learn concrete noun concepts. And indeed, I think there's this notion that a lot of us have who work in this image text grounding world that certain things may be easier to learn and more concrete than other things, at least for modern natural language processing and computer vision techniques. To illustrate this point visually, say that you went out to the web and you gathered some nice multimodal data. It might look something like this. You might have gathered some images with cat-associated captions, and you may have gathered similarly some images with beautiful associated captions. And right off the bat, you can see a sort of stark difference between these two sets of images, right? So cat images, at least in terms of like the literal objects they contain, are pretty uniform. So, cat images contain cats and maybe a few other objects. In contrast, beautiful associated images are very diverse. So weddings can be beautiful, peacocks can be beautiful, sunsets can be beautiful, anything can be beautiful. And it's exactly this difference in variance that we were aiming to capture. So how do we do this? Well, we take all of the images and we pass them through a feature extractor. In our case, we used a convolutional network pre-trained for ImageNet object detection. So the resulting feature representations are biased towards capturing salient information about objects, but you could sub in any feature extractor you would like. But nonetheless, you pass all of your images through your feature extractor, and then the goal here is going to be to measure different properties about the resulting image feature space. And I've kind of suggestively clustered things according to not only our perhaps intuitions, but also what happens in the real world. In particular, it is the case that cat images tend to cluster more tightly when compared to beautiful associated images. And it's exactly this clusteredness that we came up with an algorithm to quantify. I won't get into the details of the particular algorithm that we ended up using. There are some non-trivial problems in this domain. In particular, controlling for frequency is quite difficult. But I will draw this close connection that our method has to geospatial statistics. So geospatial statisticians are folks who are often interested in measuring whether or not statistics cluster over like a 2D real-world map. This example I've shown is cancer rates on Long Island. One first pass thing researchers in geospatial statistics want to know is like, do cancer rates on Long Island have a spatial correlation? And indeed, there's a number of statistics, for example, this LISA statistic that can provide some insight into whether or not this is clustering. And our method of measuring concreteness in this high-dimensional image feature space can be viewed as sort of a high-dimensional extension of these geospatial statistics tools. Great, so enough talking about this method. I guess it's time to see some outputs. What does this thing actually score in terms of its concreteness? We ran this on Microsoft Cocoa, and according to our method, these are the most concrete word types in Microsoft Cocoa. So you can see like some things in here make sense. So like wok, for example, as the cooking instrument makes sense, like it's a big metal bowl. Perhaps this is quite concrete and we may have guessed this a priori. But there are also some like weird things in here, right? So like if you look, our algorithm has said that delta is a very concrete word in Microsoft Cocoa. Is there something wrong with our algorithm? Is there a bug? Actually, no. It turns out if you go through Microsoft Cocoa and look at every single mention of the word delta, never is it rivers, never is it like a change in something. It's always planes. So I actually went through and checked. Every time delta is mentioned in Microsoft Cocoa, it refers to a plane. And as a result, it's assigned a very high concreteness score. Indeed, there's other weird things in here. So unripe, like any fruit or vegetable could be unripe. It could be used metaphorically. A priori, you might not guess that it would be concrete in Microsoft Cocoa, but indeed, it's always bananas that are unripe, like in Microsoft Cocoa. So you can see we're sort of surfacing a cool mix of not only things that a priori we might expect to be quite visually concrete, but also dataset specific effects. To give you a fuller picture of our results, here are some somewhat concrete and some not concrete words. The paper has human judgment correlations, so like human judgments of concreteness correlate with these scores. Also, we made sure that we were not simply reconstructing word frequency, so our metric gets at something that isn't just frequency. What are the implications of these concreteness scores? Well, it turns out that the more concrete something is, according to our scoring method, the easier it is for algorithms to learn visual-textual correlations between. So here I've shown some plots, one for each of the data sets that we considered. The x-axis is the concreteness score, so as you move to the right, things get more concrete. And the y-axis is this metric of retrievability, which encapsulates how well various retrieval-style algorithms can learn associations between images and text. And you can see that in all cases, there's a positive correlation. So indeed, it's the case that like cats are much easier to learn visual textual connections between than beautiful, for example. And this holds even for like multi-layer neural networks. We tried a bunch of different retrieval representations. And so the bad news here is that like the success of our retrieval objectives are kind of largely determined by the original feature geometry, which is sort of depressing, right? So if I could tell you whether or not a machine learning algorithm, even before training, could like do well or not, this doesn't bode well for this idea that we can perform, conditional reasoning or really do anything. So this is some, we think, bad news. But there is some good news. In particular, context quite matters. If you recall back to the Microsoft Cocoa case, we were surfacing sort of dataset specific results. And indeed, it might be the case that particular concepts are learnable in different dataset contexts. So London, for example, is a top 1% concrete word in Microsoft Cocoa and thus may be learnable. The reason for this is because Microsoft Cocoa captions were constructed post hoc by annotators. So these are people who were shown a picture and asked to write a literal description of that picture. If you were a Microsoft Cocoa annotator, you might like not use the word London unless the image was like screaming London at you, right? So like you're not going to be able to guess something's London unless it's like a double-decker bus, the London Eye, Big Ben, all of this. In contrast, London is very visually dispersed in the Flickr dataset. And this is because of how London is used in this context. So it's used as a general hashtag, so like a geotag. So any image that happens to be taken in London may be tagged with this. So we might be able to learn London as a groundable concept if we're training on Microsoft Cocoa, but not so much on Flickr. I also think these results point to an open question. In particular, this is something I'm quite interested in investigating going forward. I want to know what the limits are of these sort of retrieval style algorithms at scale. So a lot of work in learning from unsupervised web data in this visual text domain kind of boils down to a retrieval style objective where you know some image co-occurred with some text and you're trying to maximize some score. And while our results suggest that like the retrieval objectives, success is largely determined by the original feature geometry, if you look at the y-axes here, none of them are at 0. I haven't told you what retrievability as a metric means, but 0 is random guessing. So even for very non-concrete words, we're doing better than random. So it's plausible that we might be able to fix this problem simply by appealing to scale, so just downloading a ton more data. And that's something that I would like to investigate going forward. Yeah, as a quick pointer, we also extend this method to not just look at word types. We also extended it to look at continuous topics. So it turns out on Wikipedia, ice hockey is a very visually concrete topic, especially in relation to linguistics, which is more visually dispersed. And indeed, people are starting to use these concreteness scores of ours for all sorts of very cool things that we didn't think of a priori. So I don't have time to get into the details for this particular paper, but the idea is that our concreteness scores offer a nice baseline for unsupervised constituency parsing. The task is you're handed an image and a sentence, and without any training data, you are to make a parse tree of that sentence. And it turns out that a greedy clustering metric in terms of spans of concrete words works quite well for this task. So people are starting to do all sorts of very cool things with these concreteness scores. But I guess backing up a little bit, concreteness is sort of just one axis along which we would like to investigate image-text communications on the web. In particular, pointing us back to this Martian Domus White taxonomy, you can see that just the single axis of concreteness isn't quite enough to capture these sorts of the diversity of relationships that's going on here. Perhaps a more direct way of getting at this question might be to go out to some social media page and like download a bunch of image text communications and then try to predict something about them. So either annotate data with a taxonomy of interest, or perhaps try to do something like popularity ranking or something like this. And indeed, there's an increasing number of studies, including our own, that have done this. So again, here people have gone out to in vivo communicative communities and have just scraped a bunch of data and are trying to predict different things about it. I think this is a very cool area. I'm going to highlight just as a case study that I think is sort of representative of the structure of a lot of these works, our work on popularity prediction. In our case, we went out to Reddit and we gathered a bunch of image and text posts from Reddit. And you can see right off the bat, there's a ton of diversity in how people use images and text to communicate. So we have this like pumpkin that's lit on fire and a story that goes along with it. I think there's some like coyness involved in this story, but certainly it's not a literal description as traditionally construed. And indeed, like the groundedness of these captions is a little bit ambiguous in a lot of these cases. And yeah, so the task we were looking at in our case, for reasons I, again, don't have time to get into, was popularity ranking. I hope you'll believe me that this is an interesting task, and it's something that one certainly can do. The input to our algorithms looks something like this. We have image caption pairs that were submitted to these communities. And the goal of our algorithm is to predict which of these things became more popular. I've shown one particular example here that I find quite cool. I'll tell you a few fun facts about this particular input example. I can tell you that these were both made to the same Reddit community. I believe it was the cute cats community, unsurprisingly. And I can tell you that they were made 13 seconds apart in real time. So these submissions were started out very much on an even footing when they were both posted in terms of the timing involved. And I can also tell you that one of these pairs got far more popular than the other one. So one of them got a few thousand upvotes, whereas the other one only got something like 10 upvotes. If we weren't on a Google Hangout call right now, I would ask for a show of hands as to which one different folks thought became much more popular. But I'll ask you to do this task mentally for now. So again, one of these became quite popular, and in your head, decide which one of these two things you think became way more popular than the other one. I'll give you a second to decide. I'm hearing some chats coming in. I'm getting some pointers to the left. Indeed, it turns out the left one became way more popular. So as a quick caveat, if you got this wrong, don't feel too bad. There's lots that goes into popularity dynamics that I don't have time to talk about, like rich get richer effects and noisy sort of processes. And it turns out that humans on average don't do perfectly. So if you got this wrong, don't feel too bad. But indeed, I agree. There is something quite compelling about this use case in this left example. And in particular, I think there's some very interesting grounding going on here. We have this idiom, the grass is always greener, and we have this physicality of these two cats whose necks are intertwined. And it's a very complicated process to map the semantics of this idiom into the grounded nature of this image. And despite the difficulty here, we were able to do it quite quickly, I assume, if we guessed that the left one was more popular. And perhaps this is the real reason why this thing, got way more popular. It's because there is this really rich mapping. So I presented this example hopefully to motivate this popularity prediction task as an interesting grounding task. I'll return to that question in a second, but to finish out sort of the prediction results section here. Oh, sorry, I should point to, we're not the first people to realize that images and text, when co-deployed in communication, can interact in sort of nonlinear ways. There's this popular theory, again from semiotics, about how images and text can multiply each other in a nonlinear fashion. And I think that's what's going on with this idiom example. But yeah, so to finish out the prediction results, we compared an image-only model, one that just looks at the images, to a text and image model. The numbers here are all accuracy numbers relative to a 50-50 random guessing baseline. And we were fortunate, right? So our multimodal model beat our unimodal model. This is great. Some folks, we released our models actually, and some folks tried to transfer them to Instagram, and we do the best of a bunch of different comparison points among those that were not trained on Instagram. So we're transferring well, this is all great. We can look at model outputs and they seem to make sense. So here are some examples from, I've omitted the captions for now, but here are some visual touch points. So the leftmost column are things that our model is scoring highly. The rightmost column are things that our model assigns a low score. And yeah, I guess the things on the left look a bit more appetizing. I don't know how I feel about bacon donuts, but nonetheless, apparently our model finds them quite appetizing. Similarly, here are the outputs on the cute animal community. They kind of make sense. And in 2017, when we wrote this paper, this is kind of where our story ended. We gathered some data, we looked at some examples, we argued that the examples were interesting because there were visual textual interactions, we did some prediction, and we called it a day. And while I'm really quite fond of works of this structure, I think we all need to be looking more about image-text communications in practice. I really want to push this field one step further in terms of evaluation capacity. In particular, I want to bring us all the way back to the very first slide I showed in this talk. I defined visual textual grounding as a collection of tasks that require connection between visual and textual content. And indeed, I think this is a similar definition that the semioticians like to use for meaning multiplication. But if you look at sort of state-of-the-art image text classification models, they're quite sophisticated and complicated and difficult to interpret. So this is an example of one of the highest performing models that I've had a chance to play around with. It's a pre-trained transformer-based model that mixes self-attention layers, mixes object detections, mixes cross-modality encoders. It's pre-trained using 4 different objectives. It's pretty involved and complicated, and it performs very well predictively, but it's a little less clear what it's doing. And indeed, I had this nagging feeling for a few years about this project that our models actually weren't doing anything all that interesting. In particular, recently we've adopted this framework from statistics about that contrasts additive models with interactive models. In particular, multimodally additive models are those that decompose as ensembles of unimodal models. And indeed, these models are not capable of doing cross-modal reasoning in any meaningful way because they decouple in this fashion. And in contrast, multimodally interactive models are those that are capable of doing more sophisticated inferences across modalities. And models like LXMERT, these big transformers, in theory are interactive. So certainly they're capable of modeling these interactions. But are they doing so for these communication tasks that we're interested in? It's hard to say, but we fortunately have developed this tool based on some prior work in statistics, and the tool is function projection. Indeed, it turns out there's this nice way of taking these very complicated models, so any neural network, LXMERT, kernel SVM, anything capable of doing cross-modal interaction, and projecting them down on this sort of less expressive space of models. So we're calling this empirical multimodally additive projection. So we're taking the predictions of our very sophisticated models and forcing them to not do any cross-modal reasoning while ensuring that the resulting projections are as close as possible to the original predictions. And you can prove nice things about this algorithm. It's implementable in like 10 lines of code. It's a simple model diagnostic to do in practice. And we tried it. So we looked at all of these tasks. I'm now switching from a row-based view to a column-based view here. So each task is now in a different column. I've put a little bit of information about each of these tasks. The thing that they share is that they're all, again, scraped from in vivo social media data. We have our metrics, higher is always better. We have our different cross-validation setups, and we have the previous state-of-the-art results for these things. It turns out if you take the latest off-the-shelf unimodal like feature extractors, concatenate the representations and feed them to a linear model, which cannot do cross-modal reasoning because it's additive, you can get state-of-the-art in like all of these tasks. So this is a little bit worrying, but what happens if you train an interactive model? This is what happens. It turns out, we tried LXMERT, we tried different neural networks, we tried even polynomial kernel SVMs, like a big throwback. This is how well our best interactive models do. And it turns out, at least for most of these tasks, you do get a small performance boost from considering these cross-modal interactions. And again, I think this is where most work these days kind of stops. But to me, again, there's still this open question of whether or not it's the cross-modal reasoning that's resulting in these performance improvements. And indeed, if you take the empirical projection of these particular models, you can see that the performance doesn't really degrade all that much, at least for a majority of these cases. We sort of have one hopeful case where the performance does go down a lot. So in that case, it seems like the model is doing interactions. But for a majority of these tasks, it's not the case that the multimodal interactions are the interesting component. And I think this kind of calls into question whether or not these tasks are really grounding tasks, right? So if grounding requires connection between images and text, and we can project away those capacity for interactions, and we do just as well, were we really doing grounding? I tend to be optimistic, so I'm hopeful that as our models get better, we'll be able to make more complex inferences. But I think this empirical projection thing shows that we still have a lot of work to do. I should, as a caveat, note that if your data set is very well balanced in a fashion that sort of forces you to learn cross-modal interactions, it's not the case that like you can project them down and not lose performance. So it is the case that these very sophisticated models can learn interactions. It's just that for these particular tasks, they're not. So there's a lot of really well-designed visual question answering data sets, for example, for which the projection does much worse. And this is because it is doing something conditionally interactive. So yeah, the big takeaway from this work is that especially if you're gathering data from social media, you really should be reporting not only model comparisons, but also the performance of this additive projection. Good. So we're sort of running low on time here, and I kind of want to wrap up with a quick summary. So yeah, today I talked about the promise and the perils of learning from visual textual web data. Again, the promise is that we can do all sorts of very cool things with this sort of data, but I think the peril is that web texts are not literal image descriptions, and a lot of our algorithms are designed and optimized for that particular setting. And so going forward, I think we're going to have to reckon with that more directly if we want to design better unsupervised learning objectives. So yeah, my two research goals are to build better grounding algorithms, my sort of machine learning goal, and then also my computational social science goal is to understand web communication. Again, I see these two as very tightly linked. If we are to build grounding algorithms using web data, it behooves us to study that web data. And also to understand that web data, we're going to need better algorithms. And yeah, I want to take this opportunity to thank my awesome co-authors on this work. And also to thank all of you for coming to this talk, especially given the strange times we live in and the strange format with which this was given. So yeah, thank you all so much for coming.
All right, maybe we can take a moment to unmute and give a bit of applause. And we have a few minutes left, so if there are any questions from the audience, now is the time.
Hey, I'm Nick. So I just want to, I just want to ask a question about the concreteness work, or sort of two questions. So it seems like the work measures concreteness with respect to a data set, as you kind of pointed out, which is interesting. I wonder if you measure the correlation of these concreteness scores with people's sort of intuitive notions of the concreteness of the nouns. And also, is it possible to collect diverse enough data that we can sort of get at this Platonic notion of concreteness?
Yeah, I'll answer your first question. So the paper does have judgments of concreteness from humans, and we do correlate with them. The way that people actually gather these sorts of human judgments of concreteness is pretty simple. Like, it's literally like a Likert scale, and like they sat people down in a room and said, here's a word, helmet. How concrete is it? Scale of 1 to 5. So I think the manner in which a lot of these human judgments of concreteness things are gathered is sort of void of context, which I think is why we're not sort of perfectly correlating with human judgments. I think if you were to provide some context for humans, like perhaps the Microsoft Cocoa context might lead to humans to judge more concrete scores for London, for example. With respect to your second question, I'm not entirely sure I precisely mean what you mean by Platonic.
Oh, I just sort of mean like if you think about like the Platonic world of ideals, you know, sort of an idealized notion, like the notion of concreteness that these annotators are getting at.
Yeah, I guess so. Part of the point of this work, I suppose, is that we think, or at least, okay, I guess I shouldn't speak for all of my co-authors. I think that concreteness is quite context specific. And I think this points to a concern I have in general, not only with my own work in quantifying concreteness, but also more broadly in the psycholinguistics literature of like how they measure concreteness with this Likert scale thing. I think this was a first step towards understanding contextual notions of concreteness, and also at least a first step towards quantifying the contextuality there. The paper has some more examples as well. But yeah, so in general, I think concreteness is very much contextual, I guess, as are most things with language. But we thought this was an interesting first pass. Yeah.
Thanks.
Any other question from the audience?
I can check chat to see. Oh, everyone was voting for left. Okay, it seems like most people got that one right.
Yeah, so I have a few questions, but maybe one of them being actually happened to be about this concreteness measure. I wonder whether you could use this in order to discover unwanted data set specific biases that we don't want. I mean, I don't know whether delta always being a plane is necessarily a good thing for the generality of the learned model.
Totally, yeah. So I think this is definitely one thing that we are hoping people are using these concreteness scores for, because like a priori, like I wouldn't have guessed that delta would have been so concrete, and yet our algorithm does surface it. And so what we did actually for a lot of these more confusing ones, we did go through and then check the data. And I think as a means of data exploration, it's quite promising as well. I've used for the other data sets as well. There's always like data set specific things that you wouldn't have guessed necessarily a priori that are revealed by this, this scoring method, yeah.
Any other question? So we're probably at time, so I will wrap up here, and let's thank the speaker again.
Awesome. Thanks so much, everyone, for coming.
Nice talk.
Cool.
Yeah, so the next meeting is with me, but how about take a break a little bit? It was great talk, by the way. I loved it.
Oh, thank you. Thank you.
Yeah, I think it starts at, let's see, 11:15.
Cool, yeah.
So it's like 15 minutes from now.
Cool, yeah, that would be perfect. I'll go get some water and take a break.
Yeah, let me check though briefly what your next meeting. Do you know when the next one starts?
Yeah, so after meeting with you, I have an hour-long gap.
Oh, you have a break, okay.
Yeah.
Let me check it. All right, so I see you in 15 minutes.
Great, awesome,
and
thanks so much.
Are you okay with the Zoom? In which case, I may send you an email.
Yes,
for my
yeah,
Zoom
I'm happy also with Zoom.
Okay,
Sure.
bye-bye.
Great, awesome, thanks so much, Ejin.